Welcome to part 3 of chapter 7. In this last part of the lecture, we're going to talk about a couple of different things. First, we're just going to kind of mention the scale of energy consumption, energy sources, just to give you an idea of where things sit. When we talk about the Big Bang, the beginning of the universe, about 10 to the 68th joules of energy, right? Energy released in a supernova, the explosion and complete disintegration of a star, 10 to the 44 joules. Annual world energy use, right? 4 times 10 to the 20th. So you look at this scale, this is much smaller than that, right? Large fusion bomb, 10 to the 16th. Hydrogen bomb, 10 to the 14th, right? Uranium bomb, 10 to the 13th, and a barrel of crude oil, 10 to the 9th joules, right? So just the order of magnitude of all the different energy sources. So, and here we talk about energy consumption and sources. So when we talk about energy consumption or the rate at which energy is used, we're talking about something called power. Power is just the work done per unit time, all right? Or energy used per unit time. Power is in a unit called watts. We use W for that. A watt is nothing other than a joule per second. Or you could say the amount of energy or the amount of work done is the total power times the amount of time that power is applied. Right? And if you want to convert to the old English units, 1 horsepower is 746 watts. 746 watts is the energy put out or consumed by about 10 bright light bulbs. It's about 1 horsepower. As I mentioned, power is also energy per unit time. And what you actually pay for when you pay your energy bill, if you pay your own electric bill, is you pay for the energy used, right? We call them the power company. Because what we have coming into our home is power, but we pay for the actual energy we use, and so the energy we use is the power consumption times the amount of time that we use it. And if you look at your bill, what you pay for is in kilowatt hours. So the energy that they use, the unit of energy used by the electric company is kilowatt hours. It's because they think in terms of the power as kilowatt, and multiplying that by an hour is a convenient scale in terms of human terms. We would be talking about kilowatt seconds in this class if we were really talking about energy consumption, not kilowatt hours. But your power company bills you for kilowatt hours. So again, power is energy over time, or power is work over time. It is the rate at which we do work or the rate at which we consume energy. Now, when we talk about this, and we talk about power and humans, right, and work and humans, we have to think of several different things, right? We have food that we get, our energy that we get from food. That would be one of those other energy sources. Energy we get from food. And where does that energy go? Well, some of it goes into work, right? Moving yourself around, things like that. That is energy that leaves the system, right? Then some of it goes into thermal energy. In fact, for human beings, a lot of it goes into thermal energy. We are warm-blooded creatures. If we were lizards, not nearly as much would go into thermal energy. Very little, in fact. And then, unfortunately, for a lot of us, a good bit of the energy we consume from food ends up being stored as fat, right? And so one of my goals is to get rid of some of my stored energy, which means I have to burn more energy than I take in for a while. And when we talk about the human body, we talk about something called the basal metabolic rate, or BMR, and that is the rate at which we consume energy just by sitting still. Right? So we consume energy just by sitting still. Why? Well, here's a big one right here. Thermal energy, right? And then there's also the work of moving our blood around. There's the work of moving our blood around so we can move oxygen around. There's the work of breathing so that we get oxygen. There's the work of simply staying upright. There are a number of different things we do that contribute to the basal metabolic rate. If we look at that, the power consumed by different organs, right, as a percent of our basal metabolic rate, you can take a look here and see, oh wow, ooh, look at the brain, right? Our brain compared to our whole skeletal muscular system is about a tie there. And I bet when you're taking a test, that number, that percentage actually goes up a bit, right? I know back when I was a student and I was taking tests, my head would actually get hot, right? Because your brain consumes a lot of sugar when you're thinking hard. And I used to dose up with a Twinkie before every test. I don't really suggest it, but it's one of those things I used to do when I was a student. So basal metabolic rate, here's the power consumption while at rest. Here's the oxygen consumption that we have by each organ. And then here's the percentage of the BMR that each organ represents. So how does that all tie together? Well, let's take a look at a Big Mac. All right. So my weight is about 890 newtons. And if we ignore my BMR, right? If we ignore my BMR and we look at eating a Big Mac and we look at how much fat is in a Big Mac, all right? So a gram of fat is about 9.3 kilocalories, or that would be a big C calories, which is 39,000 joules of energy, right? That's 1 gram of fat. Well, Big Mac has about 33 grams of fat. Now, note, I'm ignoring all the energy in the bun, right? That's from the carbohydrates. I'm ignoring all the energy that's from the protein in the cheese-like substance and the protein that's in the meat-like substance in this Big Mac. I'm ignoring those. I'm just looking at the 33 grams of fat in a Big Mac. All right. Well, to get rid of or to completely consume this 33 grams of fat that I consume when I eat a Big Mac, I have to climb 166 stories. All right, 44 meters, about 166 stories. That's a lot, right? That's a lot. 166 stories. That's a lot of work. So that gives you a scale for what does it mean when we eat, how much energy does it take to run the human body, and if I eat something that's too fatty, what are the consequences, right? Where can this energy go? Since it's really hard for me to do enough work to get rid of it all, and since, if I could voluntarily raise my body temperature to 102, that would help, but I can't do that, right? So since I can't do enough work to get rid of it, and I can't raise my body temperature to kind of help out with burning off more energy, then it ends up being stored in fat. All right, and that's the danger of not paying attention to what we eat. The other thing there, you notice when you are ill and your temperature is up, you are tired. Well, that's because you're dumping more of all the energy you bring in into thermal energy. Right? Because you're dumping more of all the energy you bring in into thermal energy, there's less energy available for doing the work of getting up and moving around and getting out of bed and fixing dinner and getting dressed, taking a shower, all that kind of stuff. Right? So just think about this in the context of what actually happens with you when you eat, when you're sick, when you're tired, all of that. Final bit, looking at the world energy consumption. Japan and the US kind of stand out here in terms of the GDP per capita, all right? And the US and Canada stand out in terms of kilowatts consumed per capita. Now, I'm going to forgive Canada a little bit because they are, it's a little cold up there during the winter. But, we stand out as consuming more energy per person than all these other countries. All right, more energy per person than all these other countries. All right, that's it for Chapter 7. See you at Chapter 8.